So thank you everyone for coming to my master's thesis defense on a 26 watt microwatt two-stage VCO mixer, VCO and mixer for direct DPSK conversion in MedRadio. So I guess let's just get started. I don't know how to get rid of this, by the way, but I don't think it's too distracting. So I'll just start with a outline of the presentation that I'm going to give. I'll give a really quick problem definition and kind of the two-sentence summary of what the work that I've done is. I'll give a little bit of motivation and background on general design practices and some details on the MedRadio standard, and then jump into the circuit design, both at a system level of how the system works as a whole and the individual components that I worked on for this work, and then go into the design methods that were used to actually implement the design, layout techniques that were used to lay it out, and then followed by results and conclusion, summary, and future work. So without further ado, the basic problem that I'm addressing here is that there's an emerging prevalence of implantable wireless technology, and for that to be fully realized and feasible, we need very low power radios to implement it. Current technologies that have been coming out over the last few years have been drastically improving in terms of power consumption, but some of them are still prohibitively high in power consumption to be realistically implemented. Typical transceiver power is currently somewhere between 5 and half a milliwatt, so that's about the range at which the current technologies operate in, and so we're trying to at least minimize some of the power consumption in some of those elements. The proposed solution is a simple and power efficient design for the medical radio receiver front end, or at least part of it, and in addition to the actual circuit design elements, I've been working on a design methodology which allows for easy integration with other components and very efficiency-centric design to ensure optimization. And so a little bit more about the motivation. Like I said, there's a growing need for low-power solutions in this area, and that's kind of exhibited by the dedicated and recently expanded frequency band that specifically for medical radio technology. Some of the sample applications are general health monitors, cardiac pacemakers, neurostimulators, and a whole variety of different medical implant technologies. Why is low power important? Well, the crux of it is that all these things have to be powered off a battery, and so if you have lower power, you don't need to replace the battery as often, and so you have less invasive surgeries. In addition to just power savings, also minimization of the technology is important for easier integration into existing sensors and everything, so that there's minimal impact when devices actually are implanted. And this is just a little graphic, so typically right now you have a lot of sensors on the outside, and hopefully the goal is to have implanted sensors for both in the hospital and also just at-home monitoring of healthcare. So a little bit about the MedRadio standard. This is the description that's given in the FCC documentation on MedRadio. And the key term here is ultra-low power. In the case of MedRadio, these are the maximum transmit powers at the various frequency bands and the duty cycles allowed. And so even though at a very small portion of the allotted frequency you have 25 microwatts as opposed to the outside bands, which are in the nanowatt range, it's still pretty low power as far as how much transmitted power can be done. In addition, the duty cycles for how many transmissions you can do are quite low, so you not only need efficient device operation, but you also need good standby current consumption, so minimizing any kind of standby currents is also important. The original implantable radio standard was called the Medical Implant Communication Services, which was established in 1999, and it covered these frequencies and was only for implantable radios. In 2009, it was expanded by adding the 401 to 402 and 405 to 406 megahertz sidebands, which are allocated for not only implantable devices, but also externally body-worn devices. So, like I said, there are very tight power constrictions, and as I mentioned before, physical space is a large concern for specifically the implantable devices. And just as a little bit of extra info, implantable devices have to be stable over a relatively low range of temperature operation compared to kind of standard
0 to 100.
Yeah, 0 to 100 devices that you have on your phone and stuff like that. So this is just
the human body doesn't go over 0 to 100 degrees.
Yeah, well, real
few people could live.
I think typical body, and I'll get into it a little bit later, but typical shifts in body temperature for a healthy person, plus or minus 1 degree Celsius. If you're really, really sick, plus or minus 3, and that's kind of the extremes. But the specification says that radios need to be working across this temperature range.
Only after the person's dead.
So what's the cover distance?
What's that?
Meters, the cover distance.
So the transmit range is typically about a meter. So it's really just for room level communication to MedRadio base station, which will pick up the information from within the room. It's not meant for a whole house or to cover a whole hospital or anything like
So
that.
a few meters.
Really, just I think it's only specified for 1 meter.
Most of the time, it's just somebody's pocket relay station.
Yeah, and so
on him, like in his pocket.
Mm-hmm. So, and that's why they included the externally worn devices, so that you could have something more powerful on your belt, for example, that could then communicate with something else.
Ilya, I'm curious about something.
Sure.
For such short distances and at that frequency, do they actually radiate electromagnetic waves, or is it proximity coupling?
No, it actually is. It is transmitting radio waves, but it's not direct coupling. Although they have had, I think, some coupling solutions for implantable devices.
This is designed for radio frequency waves, but they do have a body channel where they actually use the surface contacts of the body as a channel rather than a wireless channel.
Okay, so I don't know if you could hear
Yes,
it.
I heard that.
Okay, so you guys can hear one. And Jeff, can you hear the questions when they're asked?
For the most part, I've heard them, yeah.
Okay, let me see if maybe if I do this, you can hear them a little bit better. Small adjustments. So, with the background, are there any more questions before I move on? Okay, so with the basic motivation, a little bit of information on MedRadio covered, I'll jump right into the system design and circuit elements. Down here is the basic system that I was working on with the box in red with the specific circuit elements that I worked on in detail. The overall system is a receiver front end designed for MedRadio standard, and the primary design choice was in using a Vance Demodulator, which is a very simple and low power solution for demodulating PSK signal, so phase shift key. The primary design elements are the mixer, which is used as a downconverter and demodulator for direct downconversion. There's a VCO, which is tuned to the same frequency and phase as the incoming RF signal to be demodulated and acts as one input to the mixer. And then there's a LNAM balun uses filtering for the incoming RF signal to get it at the right power levels and convert it from a single-ended to differential signal, which is also used as the other input to the mixer. In this design, the output of the LNAM balun is also used to injection lock the VCO, and I'll get into those details in a little bit. So, and then the output has a low-pass filter to filter out any noise from the down conversion and demodulation, and then everything is just passed on to the receiver back end. So any questions on this before I move on? Take a sip of water. Alrighty. So like I said, the design is centered around a Vance Demodulator, which was originally proposed for FSK signal demodulation. This is the whole of the Vance Demodulator, and it basically works by having 2 channels separated by a 90-degree phase shift of mixing the incoming signal, and then through the use of low-pass filters, differentiators, and then mixing again, you end up with just the frequency-shifted part of the incoming RF signal. For PSK, we don't have a frequency shift, we have a phase shift as shown here. And if you can get the local oscillator tuned to the same frequency and phase as the incoming RF signal, then at the output of the mixer and low-pass filter, all you have is a steady signal which depends on the phase of the incoming RF signal. For BPSK, which is what this design is meant to demodulate, you have a phase shift of basically 0 or pi, and by using the 90-degree phase shift, you always have an output of the mixer, which is plus or minus pi over 2. So it's one of 2 states that are possible at the output here. And so the advantage of using BPSK with the frequency and phase mesh mixer is that you reduce this whole problem for FSK into 2 components, the mixer and the VCO. In order to get the VCO, or local oscillator in this case, matched to the incoming RF signal, we use injection locking, which I will show when I go into the details of the VCO itself.
So there's a feedback loop?
Yeah, so there's a feedback loop. The exact mechanism of the feedback loop isn't covered in this work.
You do carrier recovery, kind of? To be able to sync up to the carrier frequency?
Yeah, so it's a...
Okay.
Yeah, I mean, there's no... The carrier frequency doesn't change at all, so it's relatively easy to match the VCO, even just by adjusting the bias voltage on the VCO. But I'll get into the adjustment details of the VCO in the following slides. Okay? So this is the basic system, and like I said, the 2 main components are the VCO and mixer. And, oops, sorry. So for some of you who are not familiar with devices, I just put up this slide as a reminder, so when I use some terminology, the transconductance terms from the small signal model here, and then the capacitance, intrinsic capacitance of the transistors. When I say gate capacitance, I'm referring to these 2, and drain capacitance is there. There are some additional elements that are a little bit more detailed, but I didn't include all of them. So, and so the Maneatis delay cell is used as the delay cell in the VCO, and the benefits of using the Maneatis delay cell is that it's all active components, and so there's no need for any capacitors or inductors to form a LC resonant tank, and the benefit of that is being that it makes the overall design much smaller. And in additionally, there's a single control method, which is adjusting the drain voltage through this transistor M7 by adjusting the bias voltage on the gate of that transistor. So it's a fairly simple tuning method that can be implemented there using a current mirror that's digitally segmented.
So the delay is a function of both supply voltage and bias voltage. But typically you want it to be bias voltage.
Yes, yes. So there is, you can adjust the supply voltage.
But you don't want to.
But you don't want to, and for practical implementation, changing the supply voltage on a circuit with it that's part of a whole system is more difficult.
That's a parasitic effect. You know, if there's other things going on that supply voltage, you may change the phase.
Right, yeah. The idea being that the injection locking should kind of help alleviate some of those issues, so you don't have too much phase drift. But the delay cell is comprised of these switching transistors that act as the inputs here and outputs here. And then the active load transistors, there's one constant active load, and then there's the positive feedback loop formed by the cross connection here. That cross connection is what contributes this negative GM term, and I'll show how we take advantage of that negative GM term in just a little bit. The total capacitive load of this is the drain capacitances and gate capacitances, and then as well as any loading, which in this case is due to the result of the mixer, and layout capacitance.
Wiring.
Yeah, wiring capacitance via connection buses and stuff like that.
Ilya,
Yes.
I'll show my ignorance, but what is that in the M1, M1, M2, M4, and 5?
Uh-huh.
What is that circle on the gate of the transistor?
That's just to show that it's a PMOS device instead of an NMOS device. So these are PMOS up here and NMOS down here. And so...
They usually use arrows, but now it's simply just to put a little circle.
Yeah.
Because arrows are hard to do.
We don't always use arrows because it might be in a bulk CMOS process, so it's easier just to use a bubble and define it by the supply voltage.
He said that you don't always use the arrow because sometimes it's a bulk CMOS process. So it's, yeah. Okay, so this is the primary cell of the VCO, and then the VCO is formed by connecting two of these delay cells like this, with one straight connection and one cross connection. The overall transfer function for the whole loop is shown like this, with the negative term here being as a result of the cross connection. By applying the Brackhausen criteria, I'm never quite sure how to pronounce it. What is it? Barkhausen. So the Barkhausen criteria state that for oscillator, the loop gain must be unity, and the total phase shift across the loop must be 2 pi n, where n is an integer. Each of these delay cells contributes 90 degrees of phase shift, with the final 180 degrees being contributed by that negative term here as a result of the cross connection. And by forcing the first criteria on the transfer function, the steady state oscillation frequency, or the free-running oscillation frequency, is given as this function here, where the negative GM term remains. So looking at this equation, there's a way in which it can be optimized by reducing that term in the parentheses down to 0. You can reduce the entire equation to having a free-running oscillation frequency given as this. The benefit of this is that it's nearly linearly dependent on the bias voltage. By adjusting the bias voltage, you change GM of that switching transistor, and so you get a very nice way of adjusting the oscillating frequency. This helps in adjusting the frequency in such a way that it can be more easily injection locked to the incoming transmission. And in this graph here, we can see that based on the design as it was simulated, there's a nice, very large range of tuning where the MedRadio standard is really just in this middle section, and all this is auxiliary for adjustments in frequency.
What values did you use for the transconductance and the capacitance? I don't see them anywhere in here. You have a curve there. What values went into to get that curve? What values of transconductance and capacitance?
So the GM over ID value, which I'll get into, was...
you will get into...
Yeah, so I will get into the... So that'll come as part of the results and the design methods of where the actual values, I just put this up to show that there's a nice linear relationship between tuning frequencies, and also that there's a nice large range of tunability for this design.
He's going to get into the design. This is just qualitative.
Yeah.
Okay, fine.
Motivational.
Yeah.
Okay, I'm well motivated.
So, in addition to tuning by adjusting ID, the VCO can be injection locked, and injection locking currents have been used for values as small as 1 microamp of injection locking. And I think I forgot to point it out, but the injection locking happens at here, right here. So by injection locking there, you can get the frequencies to match. And it also, like I mentioned before, syncs the VCO to the frequency and phase of the incoming signal.
So what's the supply voltage here?
So for this design, we used a 1 volt supply voltage, and in the final design, there was about 26 microamps for the VCO. So that's as much as I want to get into on the VCO. If anybody has any other questions before I move on. Okay. So as far as the mixer is concerned, the design in this design we used a passive ring mixer, and the schematic for which is given here, which is a little bit hard to look at. So it's a lot easier to look at it as a set of alternating switches controlled by the local oscillator with the RF at the other end of the input. Because the local oscillator and the RF signals by design of the system are always separated by, it's either always lagging or leading by a phase shift of pi/2, looking at this, if we consider this to be 0 and then this to be 1, the local oscillator, the RF signal is always higher in this case than the local oscillator, and so the switches here are closed, and then when it shifts, these are closed and then these remain open, giving a nice binary state for the mixer. The passive ring mixer was chosen primarily because it's the most power efficient in that it doesn't consume any DC current, so it's great for the design at the cost of the conversion gain being that even under ideal conditions you're losing about 4 dB in the conversion gain, and that's for kind of an ideal system with large input signals and square waves. So in reality we're not going to achieve that, which I'll show a little bit later. And just as a design note, the size of the transistor trades off between the conversion gain and noise. So this is the even more idealized version because we have a very quick transition there. But for larger transistors, you have a smaller conversion, a worse conversion gain, but less noise, and vice versa.
I don't think you mentioned yet, what is the typical bit rate at which this device is used?
So the bit rate is, I can't think of it off the top of my head.
Is it
related to the carrier?
You're talking about tens.
What's that?
Isn't it related to the carrier frequency?
No, I mean it's not. So if you go back to the description of the MedRadio standard, it actually specifies that it's specifically for non-voice data. So the overall bit rate is fairly low. It's meant to end.
It's tens of kilobits per second.
Tens of kilobits per second. So it's not meant to carry a lot of data. Okay. So this is actually the slide on the passive ring mixer. If there are any other questions about this design. Okay. So I'm going to get into a little bit of the design methodology, starting with the GM over ID design method. The value of GM over ID is used as the primary design variable. It's a good indicator of the strength of inversion or weakness of the inversion of where the device is operating, where devices are more efficient in weak inversion and then less efficient as you go from moderate inversion into heavy inversion. The detriment of working in a very weak inversion for a device is that the devices switch slower, and so that's where the trade-off comes, where you can only be so efficient while still maintaining the necessary switching speed. The relationship between the GM over ID value and normalized current value here is maximum under weak inversion, and using these two design parameters, you can really size a whole device. The benefits of this method is that by using GM over ID combined with pre-simulated lookup tables, that it's much faster and more accurate than traditional hand calculations. The simplest of hand calculations don't really work very well when you're working in low power regions, because they don't take into account short channel effects and channel width modulation and such details. And by designing around this GM over ID value, your primary design variables are closely related to the efficiency of the device. So if you're going for a power efficient design, you really want to make sure that the GM over ID is as high as possible for the applications. The other benefit is that it's a geometry independent variable, so GM over ID can be chosen without deciding anything else. And then again, using predefined lookup tables, you can extract all the other relevant information, and then once all that data is verified, you choose the device size that will fit the criteria of the design. Okay. And so the overall design process is kind of this step-by-step here, where the first step is characterizing the devices in SPICE using Ocean scripts, which is a scripting language in SPICE, and then using a parsing script to create what we call a technology file. And this technology file is all the relevant device information like GM over ID values, switching frequencies, the parasitic capacitances, or intrinsic capacitances, I should say, and any other such details that might be relevant to the design. The limiting factor being those variables are what's contained in the model, in the device models in the simulation profiles. Then using a group of lookup functions to extract this information from the technology file, a sizing script is written to automate the actual sizing process for optimal designs. Yes?
So did you try that for NMOS and PMOS?
Yes, so the technology files contain in this, we used NMOS and PMOS devices in this technology file, as well as some of the other devices that were in the IBM 130 nanometer.
We simulated every device in the IBM library for this particular process.
Yeah, so all the devices were in the IBM process were simulated and put in the technology file, but only the NMOS and PMOS kind of standard models were used in this work.
Okay, but did you also try to vary the dimensions of the devices and then look at this CGS, the capacitances and everything are sort of related to the dimensions, right?
Yes, so they're related to the dimensions, and so the device characterization is done by varying the gate voltage, drain voltage, and also the length of the device. So the technology file, when for the lookup functions, you specify length, voltages, and then the other factors like GM over ID, depending on what it calls for. And the output is usually a width independent value, so you'll get normalized drain current, ID over W, and then using the desired value of ID, you can find the width that'll satisfy those conditions. Okay. So the sizing script is basically the last step, which uses all the device information and is accessed through the lookup functions. And so I'm not going to go through the details of all these little bits because the main work is done in the sizing script itself. And so this is kind of the general flow of the sizing script, and I'll go through the steps individually. But using the GM over ID design methodology and using GM over ID as the primary design method or design value, this script automatically generates device sizes that will satisfy the conditions set. The entire script, the benefit of using this script is that it's entirely dependent on only a few design variables, which is the device channel length, which is chosen beforehand, the desired GM over ID for the switching transistors, the delay cell current, which we're trying to minimize as much as possible, and the desired frequency of oscillation. Yes?
How do you decide on the desired GM over ID value?
So for the desired GM over ID value, we tried to find a value that was as high as possible while allowing the devices to switch fast enough. So it was kind of a little bit of an iterative process, starting with devices that were in somewhere between weak and moderate inversion, and then allowing the script to size it to decrease that value until a solution.
So you have a script that calculates the transition frequency versus a GM over ID to determine if at the particular GM over ID the transition frequency is going to be high enough to allow for oscillation.
Right. Okay.
So,
Yeah. Okay. So for this design, like I mentioned before, the higher the GM over ID value, the more efficient, but the slower it switches. And so after a little bit of iteration, the GM over ID was chosen at 23 inverse volts, which is kind of middle ground between moderate and weak inversion. So it's a pretty good point to operate in. So that's these steps here, so defining the initial design variables and making sure that it switches fast enough using the transition frequency lookup function. And then using, once the maximum allowable GM over ID value is found, those two devices, M3 and M6, which are the switching transistors, can be fully sized, and all the intrinsic capacitance is extracted. Because we defined the ID value as a design parameter alongside the GM over ID value, there are lookup functions in order to find any any intrinsic capacitances, the drain to source conductance, and any other effects that any other variables that affect the oscillation frequency. So once those are all the relevant information is extracted and the device is fully sized, we take a look at the expanded out frequency of oscillation equation down here, and we see that now all of these values here are fixed, as well as the transconductance value of the switching transistor M3, with these still needing values to be designed around. The capacitance of the mixer is calculated because we chose mixer operating point to be in weak inversion for maximum efficiency, since we weren't as concerned, since it needs to switch relatively slowly compared to the oscillating frequency. And so that was chosen as a value of 37 inverse volts. And so similarly, once that's chosen, the full design variables can be found. So with these values fixed, and like I said, the assumption is made that we're going to minimize this to be as low as possible, 0 to simplify the equation. We get to a frequency of oscillation equation here, which we then solve for the capacitance value required from the PMOS devices in order to make that work. Because these two devices are in parallel, we size them as one transistor effectively.
you probably meant load transistors. Sizing load transistors.
I think you have a typo. Lone instead of low.
Oh, yes. Yeah. Okay, if that's the worst mistake, I'm okay with that. So we size these as effectively one transistor, making sure that the capacitance here is able to be found using the technology, using reasonable values, and assuming that the first test being that this is greater than 0, because if otherwise we have to go back and resize the other transistors to make this possible. But once a capacitance value is found using a single length width transistor, it's split into the two halves that appear here by a factor here, which is inversely proportional to the width there. So, and then this factor here is looped through until this condition is actually satisfied to satisfy the assumption that this equation works. Is that good?
All at one voltage?
What's that?
And all at once supply voltage?
Yeah, so the drain to source voltage here is assumed to be about a third of the total drop from top to bottom, so it's drain to source is about a third of the volt, which ended up being true in simulations. The simulation, the script could probably be dialed in a little bit more accurately to account for the fact that it's not exactly a third of a volt drop, but it was close enough that very minor adjustments needed to be made afterwards to make it work.
What range of supply voltages do you use? This is battery powered, presumably, right?
Yeah.
So if you run a range of supply voltages, is the battery's age?
No, I mean, we didn't do that simulation, but because of the large tuning range, we're assuming that over the life of the battery, it's reasonable that we can adjust the bias current to account for any drops. Although, for the purposes of this design, we didn't really take into account what kind of battery it's powered off of or anything like that. Okay. So the results of the scripts are here, and so the main point of putting this up is to show that M2 and M5 are larger than their diode-connected parallel transistors, in order to make sure that this value actually does indeed go down to 0. So for larger device sizes, you have larger GMs, and so that takes care of making sure that this is actually small. So the main loop of the script is to find the ratio of these two widths in order to satisfy this condition. Okay. And so I'll go away from the design methods now and into some of the layout techniques that were used, unless anybody has any other questions.
Did you specify the capacitance and transconductance?
I didn't actually list those explicitly. I can add those though.
It would be nice to know what the transconductance of those transistors are, what the load capacitance is. How did you determine what the
Well,
V's
you can tell what the transconductance of the transistors is because you know the operating current is 26 milliamps for or 26 microns for the whole oscillator, and you have 2 cores, so 13 microns per core. And you know what the GMO right E of the device is, so you can figure it out.
Right, yeah, but it would have been nice to listen. What about the capacitance?
So
capacitance of all the wiring and stuff.
So I don't actually list those out explicitly. I can easily
It
add
would be
those.
nice to put a chart in there somewhere.
Okay, sure.
Show
But
what values actually you got.
okay, sure. Yeah, I can add those. But those are in the script. They're found using the lookup functions, and then the layout capacitance is estimated in the script. And then once the design is actually implemented, and I'll show here in the layout, it's extracted out and then put back more accurately into the script to ensure that it still works. Okay, so I can go ahead and add those values.
That would be nice.
I just can't think of them off the top of my head. And so the primary goals of the layout are first of all, small occupation and design area, like I mentioned, for ease of integration into devices. You want the device to be small, and also designing against the effects of process voltage and temperature variations or PVT variations. Like we had mentioned before, the temperature variations aren't really a very large concern, because even though for the min and max values, it's much smaller than typical commercially available devices need to operate within. And more realistically, plus or minus 3 degrees Celsius, around 37 degrees, covers extreme fever and extreme chills. So at that point, you're hospitalized and probably under pretty heavy monitoring anyway. So
Actually, I was thinking about that before.
Mm-hmm.
That range of temperature makes perfect sense for devices that are implanted in the chest, where they experience the internal body temperature.
Yes.
If you have devices implanted in limbs, you may go below 25 centigrade in situations where you still want to be able to monitor the limb condition. You know, if someone is exposed outdoors to extreme cold, they may be still alive, but it may be very valuable to monitor a limb that is frozen.
So
Climbing Mount Everest, stuff like that.
Yeah,
you know,
I mean,
pacemaker type.
so-
of thing.
So these values here are the specified values over which the radio has to be stable. And it's possible that it could operate outside of these conditions.
It's interesting because those apply to the chest.
Yeah, so chest and head, and at least for the moment, you know, cardiac pacemakers and sensors and stuff like that tend to be kind of in the chest cavity. So I think that that's a pretty realistic. What's that?
One thing to mention is that it doesn't ultimately matter if the temperature drifts down to much lower levels as long as the temperature is relatively constant, because we're not doing anything to compensate for temperature variation with the oscillator. So as long as it's constant, which can be presumed in the body, even if it's a little bit different, a little bit lower in the limbs than it is in the chest cavity, it's still relatively constant.
Were you able to hear that?
Yeah.
Yes, I did.
Okay.
I have a question. Since we're talking about oscillator stability, I have not heard you say anything about phase noise. With the bit rate, you're going to...
So I'll give the phase noise numbers when I get to the results of the actual post-extracted simulation. So I have those values. And so voltage variations can kind of come in a couple of different forms. First one is for long voltage supply runs, which can have non-zero resistance over very long runs, but because this circuit layout is fairly small, we're not really considering that as being a big factor, and it's accounted for in post-extracted simulations. And to protect against voltage supply noise in general, decoupling capacitors were added in the layout, which I'll show when I get to the final layout picture. So temperature and voltage variations aren't a huge concern so much as process variations. For a stable VCO, which is able to actually operate from under different process variation or process inconsistencies, which come in the form of both wafer inconsistencies like varying doping concentrations or oxide thicknesses, as well as manufacturing inconsistencies such as mask misalignment, which can change the size of the devices. In order to mitigate these, a common centroid layout technique was used. And so, for example, for the two switching transistors, M3 and M6, if they're placed side by side and you have any kind of inconsistencies across the face of the wafer, you can end up with different operating points for the two transistors. By using a common centroid layout technique, you have half of the transistor on one side and half on the other. So if there's any variation between the two halves, they're averaged out and so to speak, over the two transistors. And so while they may both end up operating out of the area that you assume that they're going to, they operate still in a very similar fashion. One of the added benefits of this is that you have increased connection points, which helps in having a balanced capacitive load when you do the actual connections. And so for common centroid to work, you need there are a couple of design requirements, which is first that you can implement a transistor using this multi-finger layout, which is not always possible if you have very small device sizes, which actually I do in this work. And then the other design criteria is that you have to share drains at the point of crossing over between transistor 1 and transistor 2. So it's not possible for all different schematics. But the overall benefit is that you have a much more design that's much more resilient against process variations. And the detriment to this is that you create a lot more capacitive load in the layout because of overlapping metal and increased via connections. But that's taken into account in the design script, so it wasn't a very large concern. And so this is the VCO layout that we ended up with, or that I ended up with. Each one of these is one of the Maneatis cells with the M7 transistor here, the two switching transistors here, and the active load transistors on top. The transistor at the bottom has a separate ground ring to protect it against noise so that you have stable current draw. And as you can see, the common centroid layout technique was used both here and the slightly modified version at the top. I say slightly modified because the drains aren't actually connected. They're just relatively close to each other, but they're not actually connected. But you still have a little bit of added benefit by having a balanced design. And so these two transistors are connected, or these two cells are connected using these buses running along the overall results of this design were actually a very balanced capacitive load between the different connections, which is good because an unbalanced capacitive load on the connecting lines could lead to an unstable oscillator that won't actually start out. So, for the mixer layout, one of the main things about the mixer layout, as I'll show in the next slide, is that the actual mixer occupies a very small area in comparison to the biasing circuitry needed for it, because resistors are big. There's really not too many ways around it. But also, common centroid is only able to be used for 2 out of the 4 transistors, the bottom pair. And the reason for this is that because the top pair didn't share drains. So it's not a very big deal for the mixer because having slightly mismatched transistors on the mixer might affect the output voltage, the conversion loss, or maybe the voltages at which it comes out might be slightly unbalanced, but it's still going to work, as opposed to the VCO, which if it has unbalanced transistors might not be able to kick off at all. One other thing that I should mention is that minimum of 2 vias was used when I connected between layers to make sure that if there are any process variations that cause vias to not function properly, there's a second via that should take care of it. And so this, there we go. So this is the full layout. So when I said that this occupies a small area in comparison to the biasing circuitry, you can see what I mean now. The total area is 39 by 49 micrometers, and that's without any external connecting pads for testing. The size can be slightly minimized by reducing some of the externally brought out connection buses for the actual implementation in the receiver front end. You don't need all the lines brought out. Down here is the bypass capacitors for the supply voltage, and then these smaller capacitors here are used to even out a little bit of the capacitive load as a result of layout, because the connections aren't balanced between the mixer and the VCO. And so that's the layout.
Did you get anybody to build it for you?
It's not actually built yet. I think we might be trying to do that at some point. But that goes under future work, actually getting the thing fabricated. And okay, so I'll go ahead and.
Do you have $12,000 sitting around for a fabrication run?
Me personally, do I have 12,000? No.
That's all. 12 for that little? Wow.
I think
It's just that you have a minimum die area that you have to buy. So.
No, I meant it was cheap, 12,000.
I think mine and your ideas are cheaper.
Well, usually if you had a company that was interested, sponsoring or supporting, had an interest, they would just do it for you.
Okay. I think my interested company is Jeff, mostly. So. Okay, so with the layout finished, I'll just move on to directly to the results. So all the results were found using post-extracted simulation, meaning that all the non-idealities as a result of the layout, such as layer capacitance and non-zero resistances in the connection buses, was taken into account, and it was tested at the nominal chest cavity body temperature of 37 degrees. Some minor adjustments needed to be made to the operating current, so after post-extracted simulations, and so this is kind of evident here where the original design was meant to work for a GM over ID value of 23 inverse volts, but after some adjustments it operated closer to 21.7 inverse volts. And this is
So when you say adjustment, what did you have to adjust?
So the primary adjustment was just to adjust the bias current that operated the VCO.
So you changed the B bias?
Yeah, so well, changing ID essentially. But yeah, by adjusting B bias away from
So you didn't change the size?
No, the size of the devices didn't need to be changed, although I could have achieved the same effect by changing the sizes and keeping the same bias current, but that involves a lot more kind of guesswork as to which exact transistor needs to be a little bit smaller and by how much. And that also would have affected the layout capacitance if I needed to change that at all.
So what was off? Like the frequency of oscillation was off?
Yeah, the frequency of oscillation was a little bit off. From the design was the script was used to design around for 403.5, which is the center of the med-band radio, and so I can't think off the top of my head by how much it was out, but it was it was just kind of finding the right voltage point to V bias point to get it oscillating at 403.5. Okay. In addition to using post-extracted simulations, the design was tested across all the process corners, and so process corners is the expected deviation from the ideal conditions of the die, and it kind of gives the extremes of what they see in the run of however many dies that they fabricate. Down here is the table of the adjustments. So under typical operating conditions, at supply voltage of 1 volt and ID and a supply current of 26 microamps, this was the GM over ID value at which it operated, and then this was the output voltage swing or amplitude of the VCO output. In the slow corner, the supply voltage needed to be raised a little bit, and the GM over ID value also needed to be raised. And that's because under slow conditions, the transistors operate slightly less efficiently, and so they needed a little bit more voltage and current to achieve the same effect, while maintaining a fairly similar output voltage swing. Under the fast corner, the devices actually operated more efficiently, so overall they required less power, the smaller voltage swing, but the output voltage swing was much lower. So even though they're more efficient, the device...
So the goal here was just to make sure the oscillation frequency is constant, but you
Yeah.
didn't really focus on constant output.
Right, exactly. So these tests were done just to ensure that under fabrication the device could be used across all the fabrication corners in some element or another. Ideally, the goal is to not change the supply voltage because that's a little bit harder to implement in the real design. And the slow corner and the fast corner kind of cover the very extremes where it's more likely that any deviations will be still closer to the typical corners, and so you could get away with only adjusting the bias current and not the supply voltage.
Yeah, I mean, it would be fairly easy to adjust the supply voltage and the cost of power. You'd need basically just an individual LDO to run to supply the current for the oscillator. So you want to avoid that.
Okay. So the fast corners produces more efficient transistors, but with a cost of having a smaller output voltage swing, which I'll explain why that's important. For the VCO, the free-running phase noise at a 1 megahertz offset frequency for the free-running is given as this line here, and at 1 megahertz it's minus 52 dBc per hertz. When it's injection locked using a 1 microamp injection locking signal, the phase noise drastically improves to minus 118 dBc per hertz, and additionally it's also significantly more flat across, so it's good overall, whereas, for example, this is a much more steep slope, so the variation in phase noise is higher. And so...
Ilya, if I could make a comment.
Sure.
The reason I was asking about the bit rate is that at such low bit rates, phase noise is very important.
Yeah.
it might be, my gut feeling is that if you're going to operate at a 10 kilohertz bit rate, now depending on what method you use for demodulation, phase noise at 1 to 10 kilohertz is much more relevant than phase noise at 1 megahertz.
Okay.
That does really not tell me much about what happens when I use it at 10 kilobits per second.
Okay. So I don't think that I simulated down to.
I think you should have 100 phase noise at 100 kilohertz. That was the tests that we were running were at 100 kilobits per second, just trying to get the bit efficiency, energy per bit up.
Were you able to?
Not fully. So you said that the test was done at 100 kilobits per second, not 10.
100 kilobits per second, right, Jeff? You said?
I'd have to look to see what you did in the MATLAB script, or what we did in the MATLAB script to generate the data, but it was in the hundreds of kilobits range. It's typical communication bandwidth is in the tens of kilohertz to hundreds of kilohertz bandwidth.
Okay, so for communication bandwidth in the 10 to 100 kilohertz range, that's the range in which you want to look at your phase noise.
Okay. Okay. So, yeah. Although I think that given that this is a fairly flat line, I think you could actually probably extend it out to see that.
Extrapolating, of course, is the best thing that you can do if you don't have data in the desired range, but it's fraught with the peril.
Sure. Okay, so that's a good point. It's worthwhile to rerun that test at lower phase noise.
Yeah, the other issue is that the close-in phase noise is going to be dominated by whatever the I mean, we're assuming that we have a fairly clean injection signal, and so the injection signal is really going to dominate the close-in phase noise, is what I would assume.
Yeah.
Well, yes, the question is what kind of demodulation scheme you assume. If you have an injection signal, then the phase noise of the oscillator matters less.
Right.
But it's unclear to me in the overall system design where the injection signal comes from.
Right. So for the purposes of the simulations that I ran, I just had an independent source in simulation used as the injection lock signal.
But in an actual application inside the chest cavity, you don't have a reference coming from the outside.
Right.
So
no, the reference indeed would be coming from the outside. You'd have an LNA in front of the system, and the LNA would be providing injection current from a strong walking signal. It's also ultimately would be used to charge a charge pump that this thing would run off of.
Yeah, but that's what I'm saying. You have to assume a specific demodulation scheme. If the signal that comes in has a pilot, I think that's what we're talking about. In other words, it's VPSK plus a pilot, right? If it's
Jeff, did you catch that?
Yeah.
If it's VPSK with a suppressed carrier, then you do not have anything to inject.
Right.
So I'm assuming we're talking about PSK with an unsuppressed carrier, with a pilot.
Yes.
But then you have to look at the strength of the pilot. All I'm saying is to establish whether the phase noise is good or bad cannot be done in isolation. You have to look at what the receiver system requires given the modulation scheme.
Right.
Yes.
So that's correct. But I can rerun those in order to find the phase noise at lower offset frequencies to give slightly more relevant numbers. And actually, so in the comparison that I'm about to give, there are a couple of other numbers that are relevant. But the figure of merit that I use for the VCOs is given here, and it's a function of the relationship between the frequency of oscillation and the offset frequency, the power at which the device operates, and also the phase noise as given here. And so using a couple of comparisons from some other works that have been published in recent years, while operating at power milliwatts about an order and a half, or at least an order of magnitude lower figure of merit is achieved that's competitive against, or slightly higher than some of the other works. The primary reason for this is that because the power is a solid order of magnitude less, and I'm mostly comparing to injection locking because the realistic system wouldn't run under free-running conditions to actually demodulate signals with a phase noise like this. So this is just a slight table, a small comparison table. The reason that I've included this reference number 4 here is that because it uses the same VCO architecture as what I'm using, which is a 2-stage Maneatis cell. However, it's not really being used for the same applications. They're significantly different.
So they also operated in a MedRadio version? Reference 4?
I'd have to double check. I'm not sure that they give those values specifically. Although the main goal of this work actually wasn't necessarily, it was designed as an ultra wideband, so it had a very, very large tuning range, which wasn't necessarily design criteria for this. So, for the mixer results, there are 2 important graphs that I'm showing here, which is the conversion gain, which ideally is about here, but more realistically, we're operating about in this range, which is slightly a good deal lower than the ideal scenario, but also is kind of comes with the territory of using a passive filter, in that it's very hard to achieve good conversion gain using these devices under non-ideal conditions. In order to actually get a higher output, we would need a much stronger local oscillator, which would kind of require a lot more power to be drawn from the supply, and thereby negating the benefits of using the passive mixer by just having a much stronger VCO power requirement. And so, like I said, the compromise was made between device size for conversion gain and noise. And I'll show the noise output of the mixer and when it demodulates a signal in just the next slide. From the slide about medband radio, the maximum transmit power of MedRadio is at minus 16 dBm, which is around here, which is a little bit less than the ideal operating point for the RF power, which is represented by the 1 dB compression point, at which the output saturates in reference to the RF input power. But because there is a LNA at the input before it's fed into the mixer, that takes care of solving that problem. Okay. And so this is a sample demodulation of a DPSK signal. Like I said before, it uses post-extracted simulation at 37 degrees Celsius and 1 microamp injection locking signal. And this is at the center frequency of 403.5 megahertz, and the PSK signal was generated in MATLAB. So the output voltage swing of the mixer isn't very large. It's about plus or minus from 10 millivolts to minus 10 millivolts. But it's relatively small noise, and this is after the low-pass filter, and a fairly clean demodulated signal is generated.
Yeah, this is just simulation of the mixer, right?
This is simulation of the mixer working with the injection lock VCO.
But you're assuming that the VCO has a clean
injection
reference.
lock. Yeah. Mm-hmm. Yeah. So this is assuming in the simulation it's just an independent supply.
In other words, the phase noise is coming expressly from the oscillator itself, but any reference is going to be cleaner than low power DC oscillator.
Okay.
I missed the last sentence.
Could you repeat that? Just I think the connection got a little slow.
Yeah, any reference that we use is going to be cleaner than a 2-stage ring oscillator. So the ring oscillator should be contributing the majority of the noise.
Let me ask you another question.
Sure.
The reference, the control voltage for the VCO, did you assume any noise on that control voltage, or is it assumed to be perfectly accurate?
So
in the simulation.
for the purpose of the simulation, it was assumed to be perfectly accurate. The way in which that'll probably be implemented in a realistic design is using a digitally segmented current mirror, and so you can have a couple of different transistors. Each of those transistors could be designed and laid out in such a way that they're fairly good against noise by using redundant guard rings to tie them
And you have
together.
enough capacitance on it to quiet it as well.
Yeah.
Well, but that's the gist of my question. The bit rate at which this is operated is crucial. If we're talking about, say, 10 to 100 kilobits per second, any noise in that frequency range on the control voltage is going to cause additional phase noise. And you have such a high sensitivity. I mean, I was looking at the range over the space of like 100 millivolts. You go several hundred megahertz, if I recall correctly, right? With such a high sensitivity like that, any amount of noise, you need a pretty fat capacitor on that line in order to assume that it is constant. So I'd be curious to see an analysis of sensitivity due to noise in the semiconductors that drive that voltage in that frequency range.
Sure. That's a good point. For the purpose of the design, the injection locking system was idealized was the supply voltage and the biasing voltage for that transistor. But like Jeff had brought up earlier, any reference is going to be better than the free running VCO. So we gain a little bit there.
Yeah, well, and I'd also mention that any standard bias circuitry layout is going to take into account that voltage needs to be stable, just as it would on any type of differential circuit that's driven by any type of differential circuit that's driven with a tail current source. That tail current source is very sensitive to changes in voltage, as the transistors are. They're current sources that are very sensitive to changes in voltage. So it would definitely have a significant amount of decoupling capacitance on it.
Okay. So that about brings me up to the end. I think we kind of covered some of the main points, which is the problem of trying to design a low power solution to demodulating DPSK signals, using and then combining the GM over ID method with design scripts in order to maximize the efficiency of the devices. Like we had mentioned before, future work kind of includes actually getting this fabricated, as well as the inclusion of the LNA and Bowlin, as well as the remainder of the receiver backend into the design. Okay, any questions?